Welcome everybody to podcast number 4, which is where we're going to talk about percent ionization and using that to determine approximations that we might use when we calculate Ka values and why we might do that. So the percent ionization can be calculated as shown here, that it is the H plus concentration at equilibria divided by the initial amount of weak acid that you started with. All right, and then we're going to multiply that by 100 in order for us to get a percentage. Right, and again, right, this is where we have our generic equation here. So whatever we have for our weak acid, we could plug in there. Well, the reason that we're going to introduce these approximations as we calculate our values for weak acids, and we're going to do the same thing for weak bases eventually, is that the value for our weak acid equilibria constant isn't actually known super well. It's hard for us to calculate these things because the weak acids are constantly ionizing a little bit here and there, and so we get fluctuations and they're hard to calculate. So we only really know them within about plus or minus 5%. And so if we only know that within about plus or minus 5%, then the overall values that we're going to come up with can only be known within about plus or minus 5%. Then the amount of it ionizing can only be known within about that amount. So, right, when we calculate Ka, right, we have seen Ka written another way already. And so hopefully we've seen that Ka is equal to our H plus squared divided by our HB. Okay, and technically what we didn't probably write in, but this is a K, so these were all at equilibria. Another way of writing this equation is here, that Ka is equal to H plus squared divided by our HB concentration, right, initial. And these are at equilibria, right? Because if we thought about it, right, we have our HB is going to come to equilibria with H plus and our B minus, like so. So the amount of HB that's left would be the initial amount minus however much H plus is, because, right, those are all 1 to 1. All right, well, if it's going to ionize just a really small amount, then we might be able to shorthand this thing and approximate it. So we don't have to do quite as much calculation. That's going to help us out, I promise us, in a little bit. And the way we can figure out whether or not we can approximate it are these two guys here. All right, if our H plus concentration, all right, and that would be at equilibria, divided by our initial concentration of our weak acid is less than or equal to 5%, or less than or equal to 0.05, or the Ka divided by our initial concentration of weak acid is less than or equal to 2.5 times 10 to the minus third, which is also 5%, then we can do, if these are true, if true, we can approximate. And we're going to want to approximate, I promise you that. So if our weak acid ionizes more than 5%, and luckily not that many of them do ionize more than 5%, but if it does, well then we are going to have to do a quadratic equation to solve for it. And we could plug all of the things in here. This equation would get us home, but doing this is much more difficult than just the straightforward approach that we're going to do if it ionizes less than 5%. We will never use the quadratic on exams anywhere. Okay, so always less than 5% on exams. Okay, so you can make that assumption. All right, but we might need to show and prove that that assumption was okay. And we'll do that in our sample problem coming up. Well, let's work a sample problem where I've got benzoic acid, and so we're going to calculate the pH and the percent ionization of this benzoic acid. So this is one of our in-depth problems, so we're going to follow it along step by step with my numbers that are there. So it says, when benzoic acid is in an aqueous solution, the following reaction occurs. So what this is telling us is that benzoic acid is not one of our strong acids. I couldn't tell you off the top of my head what the formula was for benzoic acid. I could look it up and I could write it out pretty easily, but we don't need that. All we need is that benzoic acid, which we're going to show as being our weak acid. So this is benzoic acid for our purposes. So that's our benzoic acid. It is going to come to equilibria with some H plus and some of its conjugate base, whatever the heck that is. All right, and so just like anything, then our Ka for this is going to be our H plus times our B minus over our HB concentration. All right, step 2 says, let's start by calculating that's the initial HB concentration from our given information. All right, so we need a concentration, so that's moles per liter. So we have 0.288 moles of our benzoic acid, which we're calling HB for the purposes of this, divided by our volume, 0.726 liters. And so we're going to end up with 0.397 molar. All right, now we're going to set up our ice table here to get all of our equilibria concentrations. So I've got my ice table, so I'm going to put ice in here, and we have our benzoic acid, we've got our H plus, and we've got our B minus up here. I like to write my equation up there just to remind myself what's in each column. And so my HB, that is 0.397, and we don't have any products yet, right, when we start. All right, notice in this case that we don't have the pH like we did in our earlier problem that we worked. So I don't know any equilibria things. All right, so we're going to have to find equilibria another way. Well, let's resort back to what we did in our equilibria chapter when we didn't know anything. Let's just say, okay, let's put them in as a single unknown. So let's say that the HB has to be going down by some amount. We're going to call that X. And the products are going to be going up by some amount that we're going to call X. So we have 0.397 minus X, and we have X and X. All right, let's move on to our next page then and play this out. All right, number 4 says now we can substitute the equilibria concentrations into our Ka. All right, it says that we're going to assume that X is really tiny. So we're going to assume that this ionizes less than 5% is basically what that's telling us. All right, so what that's going to give us then is we have our Ka is equal to, all right, well, we know the value for that is 6.6 times 10 to the minus 5th. All right, and so that's equal to, well, our H plus and our B are on the top, so X times X divided by our 0.397 minus X. Okay, now if we're going to assume this, okay, then we're going to get rid of that factor there. And this is going to simplify to be that Ka is 6.6 times 10 to the minus 5th is equal to X squared divided by 0.397. And so we can then calculate through and we can find that our X is going to be equal to 5.1 times 10 to the minus 3rd. All right, well, notice that our X is also our H plus concentration. Now, number 5 says that the value of X is much less than 0.397. But let's double check that percent ionization and make sure that this is less than 5%. So our percent ionization is equal to our H plus concentration at equilibria divided by our initial HB times 100. So we have our 5.1 times 10 to the minus third over 0.397 times 100, and that is going to be 1.3%, which is lower than 5%. All right, so the assumption was okay. All right, if it wasn't okay, we would have to go back up and do this equation with that included in there, which would make this a quadratic. All right, but the assumption was okay, so it was all right for us to throw that out, thus making this not a quadratic problem. So now we can finally say, okay, the H plus was right. So now we can find the pH by doing the negative log of our 5.1 times 10 to the minus third, which is going to be 2.29 as our answer there. All right, so that is doing percent ionizations to make sure that we can make these assumptions so that we don't have to do quadratic problems. Right, in our next podcast, we're going to look at a weak acid that is a polyprotic acid and how that affects our calculations.